All right, so the final chapter that we're going to cover in class is the chapter 9 on counting and probability. And you can count small numbers, but when it comes to large numbers, it's easier to, there are easier methods for counting large numbers and combinations. Introduction to probability. Imagine tossing 2 coins and observing whether 0, 1, or 2 heads are obtained. It would be natural to guess that each of these events occurs about 1/3 of the time, but in fact this is not the case. Table 911 shows the actual data obtained from tossing 2 quarters 50 times. As you can see, more times only 1 is obtained, and 2 or 0 heads happen approximately the same amount of time. To formalize this analysis and to extend it to more complex situations, we introduce the notion of random process, sample space, event, and probability. To say that a process is random means that when it takes place, one outcome from some set of outcomes is sure to occur. But it is impossible to predict with certainty which outcome that will be. For instance, if an ordinary person performs the experiment of tossing an ordinary coin into the air and allowing it to fall flat on the ground, it can be predicted with certainty that the coin will land either heads up or tails up. But it is not known for sure whether heads or tails will occur. We restricted this experiment to ordinary people because a skilled magician can toss a coin in a way that appears random but is not. And a physicist equipped with first-rate measuring devices may be able to analyze all the forces on the coin and predict correctly its landing position. Just a few of many examples of random processes or experiments are choosing winners in state lotteries, selecting respondents in public opinion polls, and choosing subjects to receive treatments or serve as controls in medical experiments. The set of outcomes that can result from a random process or experiment is called a sample space. A sample space is the set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. In the case where an experiment has finitely many outcomes and all outcomes are equally likely to occur, the probability of an event is just the ratio of the number of outcomes in the event to the total number of outcomes. Equally likely probability formula. If S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, denoted P of E, is the number of outcomes in E and the total number of outcomes in S. So, with this notation, for any finite set of A, N of A denotes the number of elements in A. With this notation, the equally likely probability formula becomes P of E equals N of E over N of S. So an ordinary deck of cards contains 52 cards divided into 4 suits. The red suits are diamonds and hearts, and the black suits are clubs and spades. Each suit contains 13 cards. Ace through king, and jack, queen, and king are called face cards. Mathematician Percy Diaconis worked with David Aldous in 1986 and Dave Bayer in 1992, showed that 7 shuffles are needed to thoroughly mix up the cards in an ordinary deck. In 2000, Trepethan and his father used somewhat different definition of thoroughly mixed up to show that 6 shuffles would nearly always suffice. Now imagine that the cards in a deck have become, by some method, so thoroughly mixed up that if you spread them out face down and pick one at random, you are as likely to get any one card as any other. What is the sample space of outcomes? All the different cards, different combinations of suits and faces. So what is the event that the chosen card would be a black face card? Well, that would be, there's 6 out of 52, so what is the probability that the chosen card is a black face card? Well, that would be a 6 out of 52. So the outcome in the sample space S are the 52 cards in the deck. Let B be the event that a black face card is chosen. The outcomes in E are the Jack, Queen, and King of clubs and spades. And according to the description of the situation, all 52 outcomes in the sample space are equally likely. Therefore, by the equally likely probability formula, the probability that the chosen card is a black face card is 6 out of 52, or 11.5%, approximately. Counting the elements of a list. Some counting problems are as simple as counting the elements of a list. For instance, how many integers are there from 5 to 12? To answer this question, imagine going along a list of numbers from 5 to 12, counting each one in turn. Like so. And the answer would be 8. More generally, if m and n are integers and m is less than or equal to n, how many integers are there from m through n? To answer this question, note that n equals m plus n minus m, where n minus m is greater than or equal to 0. Note also that the element m plus 0 is the first element of the list. The element m plus 1 is the second element. The element m plus 2 is the third, and so on. In general, the element m plus I is the I plus 1 element of the list. So the number of elements in the list is n minus m plus 1. So if m and n are integers and m is greater or less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. How many 3-digit integers are divisible by 5? What is the probability that a randomly chosen 3-digit integer is divisible by 5? Well, imagine writing 3-digit integers in a row, noting that those that are multiples of 5 and drawing arrows between each such integer and its corresponding multiple of 5. From the sketch, it is clear that there are as many 3-digit integers that are multiples of 5 as there are integers from 20 to 199 inclusive. So, by theorem 911, okay, there are 180 such integers, hence there are 180 3-digit integers that are divisible by 5. By theorem 911, the total number of integers from 100 to 999 the 3-digit integers. 180 of these are divisible by 5. Hence, the probability that the randomly chosen 3-digit integer is divisible by 5 is 180 divided by 900, or 1/5, or 0.2, or 20%. Analysis of many computer algorithms requires skill at counting the elements of a one-dimensional array. Let A be a one-dimensional array where n is a positive integer, indicating the number of elements. Suppose the array is cut in the middle and at a middle value a sub m, so that the two subarrays are formed. How many elements does each subarray have? Well, what is the probability that a randomly chosen element of the array has an even subscript if n is odd and n is even? Well, first, the array has the same number of elements as the list of integers from 1 through m. So by 911, it has m, or m minus 1 plus 1 elements. Array 2 has the same number of elements as the list of integers from m plus 1 through n. So it has n minus m plus 1 elements. If m and n are integers and m is greater or less than or equal to n, then there are n minus m plus 1 integers from m to n inclusive. So if n is even, each even subscript starting with 2 and ending with n can be matched up with an integer from 1 to n over 2. So there are n over 2 array elements with even subscripts. Since the entire array has n elements, the probability that a randomly chosen element has an even subscript is 1 over 2. N divided by 2 over 2, or over n. So you get 1/2. If the array is even, has an even number of elements. If n is odd, then the greatest even subscript of the array is n minus 1. So there are as many even subscripts between 1 and n as there are from 2 through n minus 1. Then the reasoning of 1 or I can be used to conclude that there are n minus 1 all over 2 array elements with even subscripts. Since the array has n elements, the probability that a randomly chosen element has an even subscript is n minus 1 over 2n. Observe that as n gets larger and larger, this probability gets closer and closer to 1/2. Note that the answers to 1 and 2 can be combined using the floor notation. By theorem 462, the number of array elements with even subscripts is the floor value of n over 2. So the probability that the randomly chosen element has an even subscript is the floor of n over 2 over n. And that'll be it for the first section. And I'll do the second section here. Possibility trees and the multiplication rule. So where we started getting into counting a little bit. A tree structure is a useful tool for keeping systematic track of all possibilities and situations in which events happen in order. The following example shows how to use such a structure to count the number of different outcomes of a tournament. Teams A and B are to play each other repeatedly until one wins 2 games in a row or a total of 3 games. One way in which the tournament can be played is for A to win the first game, B to win the second, and A to win the third and fourth games. You would write it by saying A-B-A-A. How many ways can the tournament be played? So you can see where counting the individual outcomes might be challenging. Assuming that all the ways of playing the tournament are equally likely, what is the probability that 5 games are needed to determine the tournament winner? Well, the possible ways for a tournament to be played are represented by the distinct paths from the root to a leaf in the tree, shown sideways in figure 9.2.1. The label on each branch point indicates the winner of the game. The notation in parentheses indicates the winner of the tournament. So, the fact that there are 10 paths from the root of the tree to its leaves show that there are 10 possible ways for the tournament to be played. They are listed here. In 5 cases, A wins, and the other 5, B wins. The least number of games that must be played to determine a winner is 2, and the most that will be needed to be played is 5. So, all the possible ways of playing the tournament are listed in Part A, are assumed to be equally likely, and the listing shows that 5 games are needed in 4 different cases. So the probability that 5 games are needed is 4 in 10, or 2 out of 5, or 40%. The multiplication rule. Consider the following example. Suppose a computer installation has 4 input and output units, A, B, C, and D, and 3 central processing units, X, Y, and Z. Any input and output unit can be paired with any central processing unit. How many ways are there to pair an input-output unit with a central processing unit? To answer this question, imagine pairing of 2 types of units as a 2-step process. Choose the input-output unit, and then step 2, choose the CPU. Possible outcomes of this operation are illustrated in the possibility tree here, where you could see there would be 12 different possible combinations. Topmost path from the root to the leaf indicates the input-output unit A is paired with CPU X. Next lower branch indicates I/O unit A is to be paired with CPU Y, and so on. Thus, the total number of ways to pair 2 types of units is the same as the number of branches of the tree, which is 4 times 3, or 12. The idea behind this example can be used to prove the following rule. Formal proof uses mathematical induction and is left to the exercises. If an operation consists of k steps, the first step can be performed in n1 ways. The second step can be performed in n2 ways, regardless of how the first step was performed. And the kth step can be performed in n sub k ways, regardless of the preceding steps. Then the entire operation can be performed in n times n1 times n2 times whatever to times n sub k ways. A certain personal identification number is required to be a sequence of 4 symbols chosen from the 26 uppercase letters of the Roman alphabet and the 10 digits. How many different pins are possible if repetition of symbols is allowed? How many different pins are possible if repetition of symbols is not allowed? What is the probability that a pin does not have a repeated symbol, assuming that all pins are equally likely? Well, some possible pins are given here. You can think of forming a pin as a 4-step process, where each step involves placing a symbol into one of 4 positions, as shown below. So step 1 is choose symbol in position 1, step 2, position 2, etc. There is a fixed number of ways to perform each step, namely 36, regardless of how preceding steps are performed. And so, by the multiplication rule, there are 36 to the 4th power top possible pins, or just over 1.6 million. Again, for B, think of forming a pin as a 4-step process. Choose the first symbol, then the second, then the third, and then the fourth. There are 36 ways to choose the first symbol, 35 ways to choose the second, since this first symbol cannot be used again, 34 ways to choose the third, because you don't want to duplicate, and 33 ways to choose the fourth. So, thus the multiplication rule can be applied to conclude that there are 36 times 35 times 34 times 33, or 1.4 million different pins with no repeated symbol. So, for part C, there are 1.4 million pins with no repeated symbol. And by part A, there are 1.6 million pins in all. Thus, the probability that a pin is chosen at random contains no repeated symbol is 1.4 million over 1.6 million, or approximately 84% of pins have no repeated symbol. Consider the following nested loop. For I equals 1 to 4, for j equals 1 to 3. How many times will the inner loop be iterated when the algorithm is implemented and run? How many ways? How many times will these statements be run? No. The inner loop is run 4 times, and each of the inner loop is run 3 times. So it'd be 3 times 4, not 3 plus 4. So it would be 12. The outer loop is iterated 4 times. During each iteration of the outer loop, then there are 3 iterations of the inner loop. So by the multiplication rule, number of iterations of the inner loop is 12. As you can be illustrated here by the trace table shown. Permutations. A permutation is of a set of objects is an ordering of the objects in a row. For example, the set of elements A, B, and C has 6 permutations. In general, given a set of n objects, how many permutations does the set have? If they are different objects. It's a function we studied in the previous chapter, chapter 5. You have n choices here, 3. N minus 1 choices here. Oops. And n minus 2 choices there. So n times n minus 1 times n minus 2 until you get to 1. What function is that? Remember what function that was? The factorial function. 1 times 2 times 3 times 4 times 5 times 6, etc. to times n. So imagine forming a permutation as an n-step process. Choose an element to write first, choose an element to write second, etc. Any element of the set can be chosen in step 1, so there's always n ways to perform step 1. Any element except chosen in step 1 can be chosen in step 2. So there are n minus ways to perform step 2, and so forth. In general, the number of ways to perform each successive step is 1 less than the number of ways to perform the preceding step. At the point where the nth element is chosen, there's only 1 element left, so there's only 1 way to perform step n. Hence, by the multiplication rule, there are n factorial ways to perform the entire operation. In other words, there are n factorial permutations of a set of n elements. This reasoning is summarized in the following theorem. A formal proof uses mathematical induction and is left as an exercise. For any integer n with n greater than or equal to 1, the number of permutations of a set with n elements is n factorial. How many ways can the letters in the word computer be arranged in a row? How many ways can the letters in the word computer be arranged if the letters C and O must remain next to each other in order as a unit? If the letters of the word computer are randomly arranged in a row, what is the probability that the letters C and O remain next to each other in order as a unit? Well, all 8 letters in the word computer are distinct, so the number of ways in which you can arrange the letters equals the number of permutations of a set of 8 elements, which is 40,320, or 8 factorial. If the letter group CO is treated as a unit, then there are effectively only 7 objects that are to be arranged in a row. Hence, there are as many ways as to write letters as there are permutations of a set of 7 elements, namely 5,040, or 7 factorial. When the letters are arranged randomly in a row, the total number of arrangements, 40,000 plus, by part A, and the number of arrangements with the letters CO next to each other as a unit is 5,040. Thus, the probability is is exactly 1/8, or 12.5%. Permutations of selected elements. Given the set ABC, There are 6 ways to select letters from the set and write them in order. Each such ordering of 2 elements is called a 2 permutation of A, B, and C. So the definition, an R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. The number of R permutations of a set of n elements is denoted as P of n and R. If n and R are integers and R is greater than or equal to 1 but less than or equal to n, then the number of R permutations of a set of n elements is given by the formula n times n minus 1 times n minus 2 times etc. to times n minus R plus 1. Or equivalently, n factorial over n minus R factorial. So there's that factorial again. Evaluate 5 permutation P of 5 and 2. How many 4 permutations are there of a set of 7 objects? How many 5 permutations are there of a set of 5 objects? Well, just do the substitution. 5 factorial over 5 minus 2 factorial is 5 times 4 times 3 factorial over 3 factorial, which equals 20. And the number of 4 permutations of a set of 7 objects is 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. The 3 factorials cancel out, leaving you with 840. The number of 5 permutations of a set of 5 objects is just 5 factorial. Note that the definition of a 0 factorial as 1 makes the calculation come out as it should. For the number of 5 permutations of a set of 5 objects is certainly equal to the number of permutations of the set. That one wasn't as long as I was expecting it to be. Yeah, we can do one more, I think. Yeah. Come on now, cooperate. All right. Counting and probability, section 3. Counting elements of disjoint sets. The addition rule. Well, in this section, we'll look at counting problems that can be solved by counting the number of elements in the union of 2 sets, the difference of 2 sets, and the intersection of 2 sets. The basic rule underlying the calculation of the number of elements in a union or difference or intersection is the addition rule. This rule states that the number of elements in a union of mutually disjoint finite sets equals to the sum of the number of elements in each of the component sets. So the addition rule is for a finite set A, if it's the union of k distinct mutually disjoint subsets, A1, A2, etc. to AK, n of A equals n of A1, A2, all the way up to n of AK, A sub k. How many 3-digit integers from 100 to 999 are divisible by 5? Well, The solution to this problem uses the addition rule. Integers that are divisible by 5 end in either 5 or 0. Thus, the set of all 3-digit numbers that are divisible by 5 can be split into 2 mutually disjoint subsets, a sub 1 and a sub 2, as shown here. The set of 3-digit integers that end in 0, and the set of 3-digit integers that end in 5. Well, the intersection of those two is the empty set, so they are disjoint. Now there are as many 3-digit integers from 0 that end in 0 as there are possible choices for the leftmost and middle digits, because the rightmost digit must be 0. As illustrated below, there are 9 choices for the leftmost digit, 1 through 9, and 10 choices for the middle digit, 0 through 9. Hence, n of a sub 1 is 90. 9 times 10. Similar reasoning shows that there are as many 3-digit integers that end in 5 as there are possible choices for the leftmost and middle digits, which are the same as for the integers that end in 0. So, the number of elements in A2 is 90. So the total number of 3-digit integers that are divisible by 5 would be n of A1 plus the n of A2, or 180. So now the difference rule. An important consequence of the addition rule is the fact that if the number of elements in a set A and the number of in a subset B of A are both known, then the number of elements that are in A but not in B can be computed. Just a simple difference. N of A minus B equals N of A minus N of B. The difference rule holds for the following reason. If B is a subset of A, then the two sets, B and A minus B, have no elements in common. And the union of B and A minus B equals A. Hence, by the addition rule, n of B plus n of A minus B equals n of A. Subtracting n of B from both sides gives the equation n of A minus B equals n of A minus n of B. Consider the personal identification numbers that we described before. There are 1.6 million pins with repetition and 265,896 pins with no repeated symbol. How many pins contain at least one repeated symbol? If all pins are equally likely, what is the probability that a randomly chosen pin contains at least one repeated symbol? Well, let S be the set of all of the pins with repetition allowed, and let A be the set of pins with no repeated symbol. Then S minus A is the set of pins with at least one repeated symbol. By the difference rule, n of S minus A equals n of S minus n of A, or 1.6 million minus 1.4 million, which is about 265,000. Hence, there are 265,000 plus thousand pins that contain at least one repeated symbol. Because there are 1.6 million pins in all, and 265,000 of these contain at least one symbol, by the equally likely probability formula, the probability that a randomly chosen pin contains a repeated symbol is approximately 15.8%. Solution 2, P of A, is the probability that a randomly chosen pin has no repeated symbol. So P of S minus A is the probability that a randomly chosen pin has at least one repeated symbol. Then P of S minus A equals N of S minus A over N of S. By the difference rule, N of S minus N of A over N of S is the same thing. Law of fractions, separate them, and you get 1 minus P of A, the definition of probability in the equally likely case. 1 minus 0.842 from example 922 is approximately equal to 0.158 or 15.8%. The formula for the probability of a complement of an event: if S is a finite sample space and A is an event in S, then the probability of the probability of the complement of A is equal to 1 minus the probability of A, where the probability of A, or the complement of A, is equal to S minus A, the complement of A in S. A certain computer access password consists of 3 through 5 uppercase letters chosen from the 26 letters of the alphabet, with repetition allowed. How many different passwords are possible? How many different passwords have no repeated letter? How many different passwords have at least one repeated letter? If all passwords are equally likely, what is the probability that a randomly chosen password has at least one repeated letter? Counting all this, by standard methods would be a challenge. These are easier ways. The set of all passwords can be partitioned into 3 subsets, consisting of passwords with lengths 3, 4, and 5. So the addition rule says that the total number of passwords equals the number of length 3 plus the number of length 4 and the number with length 5. The multiplication rule can be used to compute the number of passwords for each length. Thus, the number of passwords with length 3 is 26 to the 3rd power. Number of passwords with length 4 is 26 to the 4th. Number of passwords with length 5 is 26 to the 5th. So the total number of passwords is 12,355,928. Constructing a password with length 3 and no repeated letter is a 3-step process where you have 26 choices, then 25, then 24. Similarly, there are 26 times 25 times 24 times 23 passwords with length 4, and 26 times 25 times 24 times 23 times 22 passwords with length 5 with no repeated letter. So the total number of passwords with no repeated letter is about 8.2 million. By part A, the total number of passwords is 12.3 million. And by part B, 8.2 million of these passwords do not have a repeated letter. Thus, by the difference rule, The number of passwords with at least one repeated letter is approximately 4 million. Given the assumption that all passwords are equally likely, the equally likely probability formula can be used. So the probability that a randomly chosen password has at least one repeated letter is total number of passwords into the number of passwords with no repeated letter, or approximately 33.1%. The inclusion-exclusion rule. The addition rule says how many elements are in a union of sets that are mutually disjoint. Now consider the question of how to determine the number of elements in a union of sets where some of the sets overlap. For simplicity, begin looking at the union of sets A and B here. You can see that there is an intersection. The intersection of A and B is not null. So, the inclusion-exclusion rule for 2 or 3 sets is the number of number of elements of A union B equals the number in B minus the number in the intersection of A and B, and by extension the extend that to 3 sets here. How many integers from 1 through 1,000 are multiples of 3 or multiples of 5? How many integers from 1 through 1,000 are neither multiples of 3 nor multiples of 5? Now, set of all integers from 1 through 1,000 that are multiples of 3, let that be set A. Let set B be the set of all integers from 1 through 1,000 that are multiples of 5. Then A union B is the set of all integers from 1 through 1,000 that are multiples of 3 or 5. A intersect B would be the set of all integers that are multiples of both 3 and 5. Which also equals the set of all integers from 1 through 1,000 that are multiples of 15. Now calculate n of A, n of B, and n of A intersect B, and use the inclusion-exclusion rule to solve for n of A union B. Because every third integer from 3 through 999 is a multiple of 3, each of these can be represented in the form of 3k for some integer k from 1 through 333. Hence, there are 333 multiples of 3, so n of A is 333. Similarly, each multiple of 5 has the form of 5k for some integer k 1 through 200. So there are 200 multiples of 5, and n of B is 200. Finally, each multiple of 15 from 1 through 1,000 has a form of 15k for some integer k 1 through 66. Hence, there are 66 multiples of 15 from 1 through 1,000. And n of intersect of A and B is equal to 66. It follows by the inclusion-exclusion rule that n union of the n of union of A and B equals n of A plus n of B plus n of A intersect B. So it's supposed to be minus, a little typo here. That's supposed to be minus n of intersect A and B, which I get right on the next line. So it'd be 333 plus 200 minus 66. Thus, 467 integers from 1 through 1,000 are multiples of 3 or multiples of 5. Almost half of them. So B, there are 1,000 integers from 1 to 1,000, and 467 of these are multiples of 3 or 5. Thus, by the set difference rule, there are 533 that are neither multiples of 3 nor multiples of 5. And that will wrap things up for the day. 20 minutes early. We got through 3 sections. Okay. Well, I didn't adjust the due date on the homework assignment, so they are the Chapter 5 homework isn't due until Thursday before class, so you have time to still have time to work on them. I guess that'll be it for the day. Have a good day. See you on Thursday.